So, measurement of skid resistance, it's not new technology in this country. This was the 1930s when a lot of research was done on it it was the predecessor to the TRRL, and this concept of a sideways force measurement system was developed. As you can see, initially it was on a motorcycle with a full compliant risk assessment for those people involved in it. And the first SCRIM, as we would recognise it, was produced in 1967, so just over 50 years old. And modern fleet come in different sizes. They've got different configurations, so the lower one has an array of other sensors measuring road condition. And the big orange one is a machine that is working in the States at the moment for Virginia Tech, where they've come to a conclusion that they need to do continual skid resistance measurement on their network because they have a alarming safety record. So, SCRIM is an acronym that stands for Sideways Force Coefficient Routine Investigation Machine, surprisingly shortened to SCRIM, but it kind of says what it does. So we're measuring a sideways force, and the sideways force, I'll show you a subsequent slide of how that's derived, is used to characterize the skidding resistance of a road surface. All of the vehicles that use the sideways force technique in this country go through an annual accreditation process at TRL. So your supplier, which may well be WDM, should be able to provide you an accreditation certificate for the vehicle that's using it. And the UK standards HD28 and the New Zealand standard, which goes by the snappy title of T10, all are based on SCRIM. Talked about correlation. The nominal test speed is 50 kilometers per hour with a speed correction between 25 and 85. So it's a device that's designed for network testing, but can also be used for more detailed investigation. We would typically expect between 100 to 200 kilometers survey a day. And there's lots of options about it. So you can have a single-sided SCRIM, you can have a double-sided SCRIM, you can put texture sensors, other sensors on them. The only constraint typically is SCRIM as a measurement process uses water, and it's mixing water with other sensors, particularly lasers, is not necessarily a happy mix. So the measurement there is test wheel there. The test wheel has no tread. It's a standard resilience tyre held at a particular pressure, so it's the scientific principle of taking out the influence of other things that may be influencing your measurement. And it's set at 20 degrees to the direction of travel. So that's three rotating, but effectively it's always trying to straighten itself, and it's that force of it trying to straighten itself, which is the force that the road is exerting on the tyre, is what we measure. Fixed load, 200 kilograms. The modern SCRIMs use a load cell, so it's a dynamic load measurement system where we're measuring the load. I think that's a 32 kilohertz system, so we're measuring that load and the sideways force continuously. Water is applied in front. Probably already dealt with the sort of simplified skidding model. So you set standards, you carry out testing, you assess the results, you investigate the results against your standards, and then you decide to either treat or not treat. And in theory, you go around in a cycle and maybe revise your standards if you find that you're investigating a lot of sites but don't feel there's a need to treat, or equally, the reverse is true. In terms of treatments, most of you will be familiar with that. Two snapshots from HD28 and HD36. HD28 is the skid standard which sets the investigatory levels, and then HD36 is a selection of materials, and that essentially puts a recommended PSV against a site category, an investigatory level, and a traffic level. There are local variations on that. Some authorities work to their own investigatory level tables or their own PSV table. But in essence, what HD36, when you drill down to it, says, once you get to an investigatory level of 0.5, you're typically getting into the area where you are looking at high friction surfacing as the material that will give you a high confidence of that skid resistance being delivered. So typically that can be approaches to junctions, it's certainly approaches to crossings, and it can be tight radius bends. In New Zealand, they apply a slightly different approach, which is an aggregate performance model. So there's a statistical review of different aggregate sources. And one of the things that HD 36 doesn't explicitly say, and this does, is it's asking you for a estimated life. So it's saying to you, what life do you want that surface to last for? And essentially it will, with an aggregate selection, characteristics of the site, it will give you a predicted SCRIM at that period of time. Whether it's a more successful approach is a point of debate. They apply a very similar set of investigatory levels, but they also have an intervention level as well, and they tend to work very much to the intervention level for those purposes. So, in terms of the highest investigatory levels, which are 0.5, 0.55 and even 0.6 in some circumstances, the recommendation in HD28 is 68 plus PSV as a minimum requirement. And in many cases, HFS, high friction surfacing, is explicitly recommended. So HD36 is leading you to potentially using these materials, but in all cases, you might have a process of departure or relaxation, which is that design process that actually evaluates individual sites and comes up with a suitable solution. If you have a departure and a relaxation process, I don't need to tell you, you need to have a record of that and how it's applied. This is a 68 PSV aggregate, and it's just a pie chart showing the recorded SCRIM levels for that aggregate. The good news is there's a reasonable amount above 0.55 and probably about 75% above 0.5. So that's reasonably good news. But there's 25% there that is not going to be meeting that 0.5 investigatory level. And as we've discovered with the review of the high friction surfacing sites, there may be any number of reasons for that. But that statistical pattern is consistent with many, many reviews that we've done of this. So we're taking a data dump from the construction records, we're taking a data dump from the SCRIM performance, comparing the two, linking them up, and we inevitably come to this similar conclusion. So essentially, even a 68 PSV, which are in ever diminishing supplies, may not be providing you the highest investigatory levels your skid policies are asking for. Why is that important? Because other research that we've done, and again we've done this for Scottish authorities, numerous English authorities, Tasmania, New Zealand, and many others, tend to show a relationship between accident rate and skid resistance. So as the skid resistance falls, the accident rate increases. The urban authority approach to crossings is a fairly linear one for that one. And the rural bends is a slightly more power relationship. So the premise of setting investigatory levels is a balance between affordability and what is I'm not going to say desirable accident rate, an acceptable accident rate. And as I say, we've done this research for a number of authorities, and we almost without fail come to very similar shapes of graphs. So this is a network analysis. This is the SCRIM difference. So it's the SCRIM difference. So we're talking about the measured skid resistance minus the investigatory level. So anything that's positive means the measured SCRIM resistance is above investigatory level. Anything that's negative is the skid resistance is below investigatory level. So this is single carriageway sites. 43% of the wet accidents are on sites below investigatory level, and 30% of the network is actually below that. So the graph tells you that once you get much below 0.05 below investigatory level, the accident rate is starting to increase. So managing the network at and around Investor Laketree is a significant safety initiative. You'll have colleagues in road safety who will look at accidents and they'll investigate causations, try to understand the circumstances of it. Yet in the background there may be a level of risk to your network just because parts of it are below investigatory level. And balancing those two approaches is something that I think a number of highway authorities do struggle with. New Zealand, I should say New Zealand do a lot of research. Everything they do is evidence-based. And they're also very good at sharing their research, which helps in sort of increasing understanding. But they've done a recent piece of research which is about managing accident rates on skid-resistant deficient sites by changing speed limits, and they've done cost-benefit analysis, taken in travel time, user costs, etc. And their research is largely suggesting that I think a 10 kilometre per hour reduction in speed is the equivalent of something like a 0.05 change in skid resistance, predicated on the fact that you need to have a realistic enforcement policy for speeding and an acceptance that people will actually adhere to the limits. And it still leaves this residual question about the 85 percentile, i.e. what about the 15% of people who will still speed? But it's a piece of work that they're developing at the moment. This is actually from Transport Scotland. So we've looked at accident rates and the severity split by site category. And what it essentially shows is bends on single carriageways, approaches to crossings and single non-events tend to have a higher proportion of fatal and serious accidents. The bend is probably self-explanatory in terms of losing control, leaving the carriageway. The approach to crossing is probably because there's a high probability you're going to hit a vulnerable user. And the single non-event might be a mix of factors in there. But essentially, it's showing that the accident rates and the severities are linked to that. And of course, where are we asking for the highest investigatory levels typically? It's on single carriageway bends and approaches to crossings. And the accident rates are also higher for the first two of those sites and approaches to junctions. So, a snapshot of an aggregate performance review. Again, this is Transport Scotland. To do this, you need good construction records. If you've not got good construction records, you can't do this. And good construction records means you know the location, the time it was laid, the material, the aggregate source, and so on and so forth. But this is PSVs against distribution of PSVs against SCRIM. And fortunately, as you go up the PSV, there is a slow march to higher skid resistance, which is what you want to show. If we then put the high friction surfacing on top of that, you can see there's a significant step sideways by almost 0.1 skid resistance level. So 0.1 becomes a very significant increase that you can achieve from that. We were, a few years ago, we were commissioned by the 33 London boroughs and Transport for London, which is an interesting environment to work in with 34 highway authorities in London. And they were very concerned about what they saw as the financial consequence of their approach to crossings and having a demand for skid resistance on them. When we've reviewed sites and prioritised sites for London, about 60% of the sites that are high priority tend to be on approaches to crossings. And they said, we've got some information about other material types that have been laid, and we'd like you to tell us, look at the skid resistance to see what the data shows. And I appreciate that's fairly difficult to see, but you've got a ULM with a 68 PSV, a 68 PSV asphalt concrete, a stone mastic asphalt. And essentially, we looked at the skid resistance over years, but that chart is summarised in there. So essentially, the high PSV aggregates, natural occurring aggregates, would give you about an 80% probability of being above 0.5 IL. In London, they do use 0.55 because of the vulnerability of pedestrians and the number of pedestrians on crossings in the city. So for the 0.55, essentially what that data was showing is the only material that's going to give you a high confidence of meeting 0.55 in particular was the high friction surfacing. That wasn't necessarily the result that the London boroughs wanted to, so we did some additional work to look at evidence. So analysis we did many years ago showed a good correlation between accident rates and skid resistance of crossings. And go back over 30 years ago now, Arthur Young published his PhD, which basically showed benefits could be achieved through the application of high friction surfacing. The TRL County Surveyors Society, as was Molasses Project, which was local safety scheme assessment, showed high friction surfacing was very successful. In London, a requirement for commissioning all new crossings is the provision of high friction surfacing, but there's no commitment to maintain that high friction surfacing. And the way that budgets are allocated in London leads some boroughs to choose not to do that effectively. So a new crossing in London will have high friction surfacing provided. Once that surface has expired its usable life, it's very much at the discretion of the borough maintenance engineers as to whether to replace it or not. And there's a drive for them to replace it with shorter length alternative materials. But the evidence that we've collected suggests that if you're targeting the highest investigatory levels, you do need to seriously look at high friction surfacing as your material of choice. The anecdotal evidence, and you've probably touched on this already, is performance is poor, it's high cost, and they don't have a ring-fence budget. So in London, they talk, we're low speed, so what is the real risk? And one of the interesting discussions we had with one borough was about King's Road. And they said, King's Road is essentially just junctions, crossings for the entire length of it. There's crossings probably every 150 metres. And they said, this environment's so controlled that we don't think high friction surfacing's required. Then talked to the accident people, and they kind of said, we have a real nighttime accident problem on on King's Road because pubs, clubs all along the length and people in various states of mental competency crossing the road. So the maintenance guys sit in daylight saying this is a very controlled environment. Nighttime, they've got a serious accident issue. And then there's this ongoing discussion about, well, aren't real skidding accidents? And I think certainly when we work with local authorities, we try to get them to look at the contributory factors, the description, to say, is it loss of control? Is it leaving the carriageway? Is it a fail to stop? Because that's all indicative of the surface condition and surface friction. And then a debate about, well, should you put 50 metres down? And their view is if they went from 50 metres to 40 or even 30, they would save significant money across London as a whole. So, highway code, stopping distances, you've got your thinking distance and your braking distance. So, highway code says, yep, you certainly could reduce the distance because the braking distance is 23 metres. But that makes assumptions about reaction time and deceleration that are probably fairly uncomfortable. Highway link design as an alternative applies a completely different reaction time and deceleration. And then the manual for streets comes up with another set of stopping distances. So there's a debate about stopping distances, but the manual for streets, if interpreted, 40 metres might be appropriate. And then there's a debate about, well, is there real benefits to just reducing it by 10 metres? We looked at 129 crossings which did have crashes, accidents, collisions, use whichever term you choose. And we reviewed the locations from the police reports relative to the crossing location. And not unexpectedly, highest number of accidents closer to the crossings, reducing as you went further away. But what we did find was there was a strange blip at between 35 and 40 metres where the accidents went up. And we didn't really have an obvious discussion, a reason for that. But I think one of the observations was people don't always cross at the crossing, they might cross in the vicinity of the crossing because they perceive it to be safer. And the concern was, you need to be putting something down that is going to provide a safe environment. And for the sake of 10 metres of material, when you've already got traffic management costs, contractor mobilisation costs, there's an argument about whether the cost-benefit ratio really stacks up. But anyway, our conclusion really was there may be a case to reduce the length of approach to crossings to 40 metres, and therefore the HFS requirement. Speed can vary greatly. We picked up some data for the length of road from Chiddock Roundabout through to Hyde Park Corner, and the speed range in one day varied on average from 10 miles an hour to over 30. And the high PSV aggregate material is laid can give high confidence of meeting 0.50 SCRIM, but will not give you that equivalent confidence of 0.55 or above. And as I said, there are fixed costs with HFS that won't vary based on site length. So there is an economic discussion about what genuinely you'll save. At the previous event in Leicester, there was a debate about braking distance and evidence that the braking distance, what the braking distances were. And there is a TRL report called PPR 815, and in it, it's got an assessment of braking distances using a braking model. And I don't profess to know what it is, but it's essentially a mathematical model to correlate braking distance with surface characteristics. So you've got skid resistance down the vertical, SMTD, and this is the distance to brake for 20 kilometers per hour, so not to a fixed, not to zero, with an initial speed of 75 kilometers per hour without ABS. Anything that's flagged up on red in there is essentially is greater than the highway code distances. The amber is about it, and the blue is less than 90% of those distances. So the question was, well, what benefit might we get if we went from a 0.45 to a 0.55 skid resistance, and at a 0.6 texture, that data saying the stopping distance will reduce by 6 metres. 6 metres could have a significant consequence on the outcome of a collision. So it's freely downloadable. It's a very good comprehensive overview of skid resistance, but there's a lot of maths in it. So I'll leave you with that to make your own decision on. But I took a virtual drive down the A82 in Scotland and looked at bits of high friction surfacing and looked at the skid resistance data. So approach to a crossing, visually not perfect, but a fairly intact high friction surfacing. And you can see the skid resistance over the years. You can see also where it picks up quite significantly at the start of that high friction surfacing. So on the basis of the data that we hold, would say that one's still performing reasonably well. It was laid apparently in 2011. As you can see, the last 10 metres it drops down significantly, which is where the end of the HFS is at the crossing. A bend, 2012, high friction surfacing, visually not as good, and there is a suggestion that the 2017 SCRIM data shows a significant drop-off. In looking at these images, you have to remember in the UK we're measuring skid resistance in the left-hand wheel path only. So on the bottom image, the deterioration is probably more marked on the right-hand wheel path. So there's always that test of how consistent is the surface, is it showing different patterns of wear. Another one looking particularly at the start, not particularly great. We don't know the age of it, but again, it doesn't look fantastic, but you'll see at the start it's not particularly great. There's not a particularly attractive patch in there, but again, it's consistently providing 0.6 skid resistance there. And another bend where there's probably less high friction surfacing and more underlying surface there. And again, you can see there's quite a significant drop from the 2015 to 2016 data. But I'm going to leave you in not so sunny New Zealand at the moment, depths of winter. But this is a site that, depending on your pronunciation, is either Petwon or Petone Overbridge. And this is a site that was for the NZTA, I think they call it their recalcitrant child. They really had issues with it. That is the accident rate per month for a period of time. So they were consistently getting accidents of upwards of 4 or 5 per month in that particular location. They resealed in March '94, accidents went. And then slowly the accidents reoccurred. So they did their first calcined bauxite treatment in New Zealand in '97. And in the 45 months afterwards, they had 2 crashes compared to the 45 months before where they had 96 crashes. So as an indication of an impact, it's one of the best studies that I've seen of that kind. And it's what they say in their context. You're coming along a dual carriageway and then you've got a tight radius bend that just tightens and tightens and tightens. And people were just basically leaving the carriageway there until the high friction surfacing was laid. This is one of our NZ clients, Mark Owen, top guy, and this was his comment about it. Essentially, they used the priciest mix of them all, calcined bauxite, crashes just dropped away. So, yeah, it's a good case study of does high friction surfacing work. So my conclusions are pretty much the studies that we've carried out, and these are from numerous highway authorities, clearly demonstrate that collision rates increase with as skid resistance falls. And the process of setting ILs is informed by that data. There was this concept that you would equalise risk, but in reality you can't equalise risk to the higher event sites. The network SCRIM testing provides data to act upon in skid strategy, and part of that process should inform aggregate selection. Just a reminder, an injury accident is valued at £76,000 in 2015 prices. So saving one accident pays for itself times over again with a high friction surfacing application. ILs of 0.50 or greater are very difficult to achieve and sustain with high PSV aggregates. And the HFS provides a significantly higher skid resistance than conventional materials. And surveys do indicate that visually poor high friction surfacing can still provide a good level of skid resistance. So whilst it might have stripped in places, that doesn't mean it's not doing the job that it was actually laid to achieve. So that really concludes what I was going to say. So thank you.